This video is going to deal with a topic called hybridization. Basically, it's our explanation of how electrons are actually able to come together to form bonds in covalent bonds. Okay, and your learning target is this one. I can use hybridization theory to identify the different shapes of the molecules. So far we've done Lewis dot, which tells us how electrons can be shared in bonds and in lone pairs to produce octets. And then we looked at molecular geometry, which is based on the VSEPR theory. Okay, if you want to reduce your electron repulsion, you make your electrons as far apart as humanly possible. What hybridization theory is our way to bring in the molecular orbitals into bonding. Because they know if we're making a bond with an electron pair, if electrons reside in orbitals, there must be an orbital when it bonds. And hopefully all of that will have a relationship with the shapes that we've seen in the Lewis dot structures we've made. Luckily it does. So what is hybridization? Think of what a hybrid is. You know the term hybrid. Hybrid usually means a combination of something. Like a hybrid car is both a gas-fueled car and an electric-fueled car in one vehicle. So a hybrid oftentimes is like a blending or a mixing of two separate things. And that's exactly what a hybrid orbital is. A hybrid orbital, a hybridization, is where you combine your s orbital and your p orbital, and you make new hybrid orbitals that have some s and some p characteristics. You can actually see how hybridization happens here.
Chemical bond formation. Hybridization is the mixing of atomic orbitals in an atom to generate a set of new atomic orbitals called hybrid orbitals. Click on one of the hybrid orbital buttons to see how hybrid orbitals are produced.
So again, what's happening here is when you're actually creating a bond, one atom's orbital and the other atom's orbital are mixing, overlapping and mixing to make a bonding orbital where the new electron pair resides. So let's see what happens when one s and one p come together.
Mixing an s orbital with one of the p orbitals generates two equivalent sp hybrid orbitals. Note that the number of hybrid orbitals is equal to the number of atomic orbitals that are hybridized. The set of two sp hybrid orbitals has a linear arrangement. The angle between the orbitals is 180 degrees.
So you've already seen this shape before, right? This was the same VSEPR shape as linear, which has the same name. It's 180 degrees apart. So the sp hybrid orbital is the same as our VSEPR linear shape. This explains how and why we have the shape we do. Okay, let's look at sp2.
Mixing an s orbital with two of the p orbitals generates three equivalent sp2 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. The set of three sp2 hybrid orbitals has a trigonal planar arrangement. The angles between the orbitals are 120 degrees.
So again, you've seen this. This is the trigonal planar that we've been dealing with the VSEPR theory. Right? And this again explains how that happens. We end up having three orbitals at the three locations. We either have our bonds or we have our bonds, okay? And now those shared pairs reside in this hybrid orbital. They don't reside in an s or a p, they reside in an sp2 orbital. Let's look at sp3.
Mixing an s orbital with the three p orbitals generates four equivalent sp3 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybrid. Hybrid orbitals has a tetrahedral arrangement. The angles between the orbitals are 109.5 degrees.
So when you have a tetrahedral shape, that's because you have sp3 hybridization. You have an s and three p orbitals all coming together, mixing up, and creating four equal orbitals where your bonding electrons reside.
Mixing an s orbital, three p orbitals, and a d orbital generates five sp3d hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals hybrid orbitals has a trigonal bipyramidal arrangement.
I don't know
The
why.
angles between orbitals are 120 degrees in the trigonal plane and 90 degrees between orbitals in the plane and those above and below the plane.
I don't know why it talks over itself. So here's your trigonal bipyramidal. So again, this Vesper shape that we already saw based on reducing electron repulsion can now be supported with our hybridization of orbitals. To make a trigonal bipyramidal shape, you take one s, 3p, and 1d orbital, mix them all together, and you make 5 new orbitals where your electrons can reside.
You can click on any of the 5 hybrid orbital shapes in the table to review that particular hybridization.
In the end, this is what you get, and I have this table actually as part of the PowerPoint notes that are online. Okay, same one. So hybridization is just an additional component to classifying chemical or molecules. Okay, you can do the Lewis dot for it. You can do its 3-dimensional Vesper shape. You can identify its shape name. And then taking it one step further, you can identify what the hybridization is depending on what number of bonds are and things like that. So if you need to make 2 bonds off the central atom and that's it, to make those 2 bonds, you're going to mix one s and one p to make a hybrid sp orbital, and that'll be linear. So if you made a molecule and it was linear, that would have sp hybridization. If you made a molecule and it was trigonal planar, so 3 bonds, no lone pairs, that hybridization would be sp2. In order to make those 3 orbitals, you need one s and 2p. Okay. If you're working with a tetrahedral, now that is 4 bonds to your center. You need an sp3. This is also the shape that you will use for bent and trigonal pyramidal because your lone pairs still need a location to go even though they're not in a bond. So you make the basic structure of a tetrahedral and you still need the sp3 hybridization. You just don't have bonded electrons in every orbital, you have some lone pairs. If you're working with the trigonal bipyramidal, you'll have sp3d hybridization, and if you have an octahedral, you'll have sp3d2. One thing you can see here that might help you is just that the number of bonds will relate to the number of orbitals you have, which he said in the video also. So you have 2 bonds, you'll always have your s, and then you'll have a p if you need 2. If you need 3, you'll always have your s, and then you'll have 2 p's to make a total of 3. If you have 4 places for electrons, you'll always have your s, and then you can have 3 p's. If you need 5, now you'll always have your s and your 3 p's, but after your 3 p's, you're done, so that's why you use a d. And then if you need 6, you have your 1s, your 3 p's, and now you just have 2 d's. And presumably that could continue to then 7 and 8 and 9 as you continue to add more d orbitals. Okay. This is another pictorial representation of how you hybridize. So instead of having the 2s and the 2p orbitals, they actually mix together and they make 4 sp3 orbitals. And you see how there's an sp3 with 4 electrons in it rather than just 2. And the reason I want to show this to you is that if you have less than 4, okay, if you have less than 4 bonds to that center, when we mix that sp2, we have an extra p left over. And that's really important because the p is how we make our double bonds. So you can't have a double bond if you have the sp3 because all the electrons are being used to bond. But if you have sp2, we have an extra p available for a double bond. And if you just have sp, we now have 2 p orbitals left over that you can potentially use for double or triple bonds. The explanation of how the orbitals make single and double bonds is what we're going to do on Monday. We'll flesh out hybridization a little bit more, but essentially it's kind of a memorization thing in that if you make your shape with Lewis dot or with the model kits and you see that it's linear, that will have sp. If you make your shape and it's trigonal planar, that will be sp2. If you make your shape and it's tetrahedral or bent or trigonal pyramidal, that will be sp3. and so on. So if you make your shape and it has 5 bonds, it just continues. Okay, so there's basically a hybridization assigned to every shape because of how the orbitals mix. Okay. Have a basic understanding of this. Have a nice weekend. I'll see you guys Monday.